So now at this point, we know the divergence test or the nth term test, and then we also know the integral test, and we know the comparison test, and the limit comparison test. And so in summary, the divergence test says that if a limit as n goes to terms of your series does not equal to 0, then the series must diverge. The integral test says that if your series converges, then your integral from the same bounds must also converge, and conversely, if your integral converges, your series must also converge. And of course, if your series diverges, then your integral diverges, and if your integral diverges, your series diverges. This is very much a two-way street. In the comparison test, we say that if we know that one series is larger, so if you have a series and you know a series that is larger than the series you have is converging, then your series must be also converging. And if you know a smaller series compared to the series you're testing for, then and the smaller series diverges, then your series also has to diverge. So we're an sigma bn and then with the limit comparison test, we're saying we're comparing the terms, and as n goes to infinity of an over bn, where bn is a sequence or series of your choosing. If this if this equals to a number, let's call it L, where L is greater than 0 but less than infinity, then we can say that an and bn have the same behavior. So if you know bn converges, then you know an converges. If you know bn diverges, then you know an diverges. Obviously, if it doesn't equal to L, then you can't make the comparison to, we can't make this comparison. And with the integral test, the comparison test, and the limit comparison test, all of these tests require that the terms of the series be greater than 0. And so there's two more tests that we're going to cover. One of them will be a highly useful test that's quite useful and important, and really it'll solve I can't say most problems, but it's quite useful. So it's called the ratio test. And the ratio test basically says that, say you have some series of an where an is greater than 0. So once again, our terms have to be positive from n equals 1 to infinity. If the limit of n as n goes to infinity of an plus 1 over an is equal to if this is less than 1, oh, I forgot the infinity. If this is less than 1, the series will converge. And if limit as n goes to infinity of an plus 1 over an greater than 1, then the series will diverge. And this is like pretty neat, because then for example, with the comparison test and with the limit comparison test, you have to go pick your own bn, and that's quite difficult in some cases. In this one, you don't have to pick an bn. You just take the an plus 1th term, so the next term, and you divide it by the current term. And if it's less than 1, then we know it converges, and if it's greater than 1, we know it diverges. So it gives you a case for convergence and a case for divergence, and you're like, Like, this is pretty cool. Like, why don't we just use this all the time? And the reason we don't use this all the time is because when the limit of n goes to infinity, when this an plus 1 over an is equal to 1, this test is inconclusive. And so this is the case that really makes all the other convergence tests useful. If it wasn't for this, for example, if these limits were always greater than 1 or less than 1, I guess less than 1 or greater than 1, then we wouldn't even need any of the other tests. We just plug every single series into our ratio test, and we would always be able to tell you if it converged or diverged. So the only reason the ratio test is not our all-encompassing test is because it is inconclusive when the limit of n goes to infinity of an plus 1 over n is equal to exactly 1, because at this point this test is inconclusive. And really, we know that this test is inconclusive because of p series, really. So when p is equal to 1 versus when p is equal to 2. For example, when p is equal to 1, we have the sum of 1 over n. P is equal to 2, we have the sum of 1 over n squared. So if we were to use a ratio test, we get limit as n goes to infinity of n over n plus 1, and this is equal to 1. And here we get as the limit as n goes to infinity, n squared plus n plus 1 squared, and this also equals to 1. And obviously, this is a converging series, we know from the p-test, and this is a diverging series, which we know from the p-test. So when this limit goes to 1, it can be either or, which is why we call this test inconclusive. And so how to one of the easiest ways to use the ratio test is kind of keep all your like terms together, and I'll show you what I mean by that in the next video when we do an example.